Thank you very much for the nice introduction and for giving me the opportunity to present this tutorial. And of course, thanks a lot to all of you guys for showing up today. So just a few words of where I'm coming from and what the background is, because actually not entirely machine learning. So my background is more knowledge representation and reasoning with the aspects of semantic web and also rule induction. So I did diploma in applied informatics at St. Petersburg State University, then moved to Newcastle for internship, did a PhD in computational logic at Vienna University, and then was a researcher at Max Planck. So now I'm a research scientist at Bosch Center for artificial intelligence. So let's just go straight into it. And before going into details, let me just say a few words about knowledge in general. So this important concept was studied by philosophers for ages, and there were many definitions. Plato claimed that knowledge is a justified true belief, true opinion, and there were many discussions on how this knowledge could be defined. But what everyone agreed on is that knowledge comes in two forms. Internal knowledge, that is essentially what is stored in our heads, and external, that is the knowledge that we all share. The idea of structuring external knowledge into graph representations dates back to Aristotle, who grouped things known to people in a set of opposing categories, like the ones you see on the slide. Later, these led to more advanced graph representations. Ancient philosophers most probably did not expect that actually these ideas would hold even these days in the context of digital knowledge. So knowledge graphs are essentially huge collections of facts extracted from the web, primarily from Wikipedia data sources, for instance. And there are many, many projects that were raised recently, including Yagor, a knowledge graph developed at Max Planck Institute for Informatics, Google Knowledge Graph, of course, Wikidata, NEL, and many other developments. Many people might not know, but in fact, you and I, we all use knowledge graphs on a daily basis when issuing simple queries on the web. For example, if you search for the winner of Australian Open 2018, instead of a syntactically similar web pages, you would actually get a concrete result, Roger Federer in this case. What happens is the query is transformed into its formal representation and issued against the graph stored at the backend of the search engine. However, for instance, if you search for something like living place of the winner of Australian Open 2018, in fact, you would only get a set of keyword-related documents. While, of course, one would prefer to be capable of issuing actually more complex queries and getting structured and concrete results. You could search, for instance, for the wife of Roger Federer. And if you look, for instance, for some of the things, like living place of Roger Federer, in fact, you would not get any results here. Now, you as a human being would think, actually, wife of Roger Federer, Mirka Federer, if we know where her place is, we would also know where the living place of Roger is. Well, now, actually, what happens is that, in fact, this indeed holds. And if we search for the living place of Mirka Federer, we will get a concrete result, Bottmingen in this case. We as humans would apply common sense and see that, in fact, given the knowledge that we have found so far, we can deduce the living place of Roger Federer, Bottmingen in this case as well. But can actually a machine use such rules and get them from anywhere? This is essentially the question that we are going to ask and answer, hopefully, in this tutorial. Where these rules could be exploited? These rules could be used not only for fact prediction, as we have just seen, but also for instance, checking truthfulness of certain facts, or data cleaning, some domain descriptions, finding certain trends in knowledge graphs. Now, before going into details, let's just have some, formal preliminaries. I won't bother you with too many technical details here, but just some few definitions that would probably help us to go through the rest. We are here talking about Horn rules. So just rules which basically do not have any negation, and it's a set of, so it's basically an implication where we have only positive atoms. So a rule is given as presented on the slide, where we have a body on the right-hand side and a head on the left. the right-hand side, the body, is essentially a conjunction of atoms. And the informal semantics is as follows. If the body of the rule is true, then the head must be true. As an example, consider a so-called ground rule, that is, rule without variables, as the one that we've seen before. So if Mirka is married to Roger and Mirka lives in Bottmingen, then Roger lives in Bottmingen too. Pretty natural. Now, these rules could also be on a non-ground level, where we have variables universally quantified. So that basically holds for all of the individuals that are in the graph. So married people live together. There could actually be also exceptions, as every rule has an exception. For instance, as some of you might know, in fact, married people live together unless one is a researcher. So basically, these kind of exceptions are also very interesting. And in fact, we want to learn rules that could potentially handle such exceptions. So this is the rule that is presented formally on the slide. So such rules could be seen under the closed world assumption, which intuitively means that whatever is not present in the graph is assumed to be false. So in this case, since if it is not known that a person is a researcher, we could apply this rule. Well, you might be thinking, there is this strange type of negation that is different from the negation that you might have learned in logic in some school years or university years. Here there are essentially two types of negation that one could, in principle, think of in the context of knowledge representation. And the first one, the one that we're talking here about, could be exemplified as follows. Imagine you are staying at a railroad crossing and you want to cross the road. One way is to say, well, at a railroad crossing, cross the road if no train is known to approach. Pretty dangerous. So it is not known that a train is approaching. Another rule would say, at a railroad crossing, cross the road if no train approaches. That is, that you know for sure that no train approaches. So there are different ways of how you treat the knowledge, how you represent it, and how you basically reason about it. What the intuitive and the internal meaning of these negations is. Right. Well, if you have a set of such rules, you could actually apply them to predict potentially missing facts. So, for instance, here we have a small program that consists of two facts. Is married to Mary John and lives in Mary Ulm. And we have a rule stating that unless one is a researcher, married people live together. Since none of these guys is known to be a researcher, we can actually apply this rule by finding substitutions of variables to constants, respectively, and then finding whatever is inferred from what we had before. So in this case, we will infer that John also lives with Mary in Ulm. Now, if we add an information that John is actually a researcher, the fact that he lives in Ulm will no longer be derived in this case. Right. So what our main goal would be is try to learn this kind of rules from knowledge graphs. And these rules are particularly useful for reasoning under incompleteness in general. So this is just a small preliminary information. Right, so let's go straight into the rule learning topic. And of course, this is not a new thing. And there were a lot of other research works done actually in the 90s already that looked into this important problem. So if one talks about different ways of reasoning with incomplete information, one could actually classify it into three groups. One is so-called default reasoning, which states that if we assume normal state of affairs, unless there is evidence to the contrary, something should hold. So by default, married people live together. There is so-called abductive reasoning, which states choose between several explanations that can explain a certain hypothesis, choose the most likely one. So for instance, we observe John and Mary live together. As an explanation for that, we might state they must be probably married. So this is the second way of reasoning. And finally, the third one, the one that we are interested in, can be stated as follows. We generalize a number of similar observations into a hypothesis. Given many examples of spouses living together, we want to generalize this knowledge into the rule that we've seen before. And this is a specific type of reasoning under incompleteness that we are looking at today. Right. So as said, that goes back to 60s and 70s, where Plotkin and several others proposed concept of generalization. And then it was developed further in 80s by Shapiro, Samut, and several others. The concept of inductive logic programming, a very important field, has been introduced in 90s, actually in London, at Imperial College by Stephen Muggleton. And then further developments in statistical relational learning in 2000s are also very relevant in our context. Right, so what kind of inductive tasks are actually out there from these 90s? Because naturally we would want to reuse some of the things in the context of knowledge graphs. So one of them is, for instance, learning from examples. So what is intuitively stated is that imagine you have examples of father relations and non-father relations given. By the way, if it is not easy to parse all of the information on the slides, don't worry. So just intuitive, understanding is important here. So what we have is that we have E plus, a set of positive examples of father relations, and E minus, a set of examples that are in a non-father relation. And in T, we store a knowledge graph, essentially. So it's just a set of facts, basically, relational facts. So these are our parent-of and male relationships. So if we want to find some rule with the two body atoms, intuitively, in this case, the appropriate one would be the parents that are male are actually fathers. So we are learning from some examples. So another concept is learning from interpretations. So in this case, we have, as an interpretation, basically our knowledge graph. And what we also have, additionally, is a set of other facts and possibly rules that do hold in the world. And what we want to learn is a set of essentially other rules that we could add to this theory that we have, such that our interpretation will become essentially a valid model of the whole program. Right, so in this example, one of the hypotheses would be the one presented on the slide. But here, conceptually, just important. So there are these two essentially main ways of learning rules from the data. Okay, so an important concept here is the concept of generalization. So what we do is essentially we generalize hypotheses, either from specific, we are going towards more general ones, or vice versa. And we traverse the hypothesis space in this way. I mean, this slide is a pretty technical one, but so don't worry if some of the details are not very clear, but I'll try to bring the intuition here. Right, so we say that if we have two facts, or two atoms basically, one is more general than the other one if there is a substitution for constants or for the variables in the first atom that would lead to the second. So here, for instance, person of X is more general than person of Roger, obviously. Right, because here X is a variable, so I say that everyone is a person. It is more general than stating that only Roger is a person. Then there is a concept of, let's say, generalization across different combinations of these atoms. So for instance, saying that everyone works everywhere is more general than stating that some person works at Bosch, some researcher works at Bosch, right? And this is the crucial thing, that there are points or there are facts that, or statements that are more general than other statements. And rule is something that is super general and generalizes what is being observed in the data. Right. So in this case, this is basically holds that the left-hand side is more general than the right-hand side because of the respective substitution. Now you could also actually apply that to whole hypothesis. So for instance, here stating that all researchers are people is more general than stating that if Matt is a researcher, then he's a person, right? This is just these concepts. Interestingly, you could also go further and consider this kind of generalizations with background knowledge. This is pretty interesting, in fact. So, for instance, if one looks at the following example, we would get the statement that there is some sort of a concept of a relative entailment. So for example, let's look at the following two facts. Roger lives in Bottmingen and Roger lives in Switzerland. Which one would be more general? Right. In fact, if you know that Bottmingen is located in Switzerland, this is not entirely true. And in fact, the first one would be more general than the second. And why that? Well, actually, if you know that Roger lives in Bottmingen, you, of course, know that he lives in Switzerland. That is why the first one is more general than the second, given additional background knowledge, which is an interesting observation. So just playing around with these generalization concepts, one could, exploit the whole search space of hypotheses. This is the main idea of all these inductive learning things. So it lies at the heart of inductive learning. And what happens is that one would ask, how would we explore the search space of hypotheses? Well, we start from something super general. For instance, in this case, everyone lives everywhere on the slide. And then we try to specialize further and further our hypothesis in order to get to something meaningful. For instance, if we add an atom, we could add an atom, unify some variables, or add another constant instead of a variable. So unify a variable to a constant, basically. So constant is some specific individual in this case, like Bob. So, and Shapiro in the 90s actually showed that in order to traverse the whole search space of hypothesis, it is sufficient to apply only these three operators. And of course, the search space of these hypotheses is enormous. So the question is how to explore it efficiently. And this is the whole task of inductive logic programming. Right. So this is a bit theoretical, maybe, to some extent. So there were some also concepts of inverse entailment proposed early on. So, and there's a whole bunch of other, specific tasks within this area. I'll just briefly mention so that you're aware of these things. So for instance, you could have tasks that are various with respect to the data from which you are learning, as discussed before, either from examples or from interpretations. You could have different types of output knowledge, either rules or some logical theories, for instance, description logic, ontologies, or something else. So you could have different ways of how data is given as input, just fact by fact, incrementally, or a whole data set altogether. Availability of Oracle and other things. Importantly, learning rules with noise present in the data is something that is a crucially relevant task in the context of inductive logic programming. And actually, it was recently studied by DeepMind. Evans and Grevenstetter proposed an approach where this is combined with the deep learning techniques, so this inductive logic programming methods. So it's getting more and more popularity, actually. Right. So now one would be asking, can we use these old-fashioned 90s techniques in general in the context of knowledge graphs, which are extracted from text? There is a statement, the goal of inductive logic programming is to develop a correct and complete algorithm which efficiently computes hypotheses. But actually, the real world is very complex and pretty noisy. So let's just look at several issues that prohibit us from directly exploiting classical inductive logic programming techniques. First of all is the open world assumption that is being applied in knowledge graphs. Intuitively, it states that the data is incomplete. That is, negative facts cannot really be derived. For instance, you never know, maybe Roger Federer is actually a researcher and doesn't live with his wife, Mirka. It is not stated in the data, but why not? Or Albert Einstein was a ballet dancer. He was a great talent, and actually he even wrote a poem about dancing. Maybe he was a dancer as well, who knows? Now, another thing is a data bias. And knowledge graph are extracted from text, which typically mentions only some interesting facts and popular entities. This goes along with the concept of man bites dog phenomena, which intuitively states is that in text you would mention that man bites a dog, but you would never mention that dog bites a man, because this is a typical thing. That is why there is this bias of the popularity. Another issue is, of course, the size. Modern knowledge graphs are enormous, so they contain about 70 billion facts. So, could we actually do still something about it? And of course, world knowledge is more complex than these perfect logical models that were introduced in 90s. So, what could we actually do in order to still learn rules from knowledge graphs? One way is to go into the direction of exploratory data analysis. So here, what one is dealing with is answering the question, how different correlations that appear in the data could be exploited and mapped to some sort of rules. Let's see what is the relevant thing in this context. So there is this classical data mining task, for instance, is as follows. Given a certain transaction database, we want to find products that were frequently bought together. So here we have different transactions and things that were bought, like apples, beer, and something else. And we could observe that out of 4 people who bought apples, actually 3 also bought beer. This is so-called association rules. So correlations could be actually seen as some sort of rules as well. And this goes back to this data mining techniques. Now what you could see here, you could just count how many apples are there in this transaction database and say the support of apples is 4 in this case. Now you could have a rule stating if you get apple, you get a beer with a certain confidence that would reflect how well, essentially, this rule describes what you observe in the data. Right. There could be some other measures that show how well these rules perform. But then, obviously, these are exploited in the context of, let's say, specific objects, but not the graphs. Of course, you could transform every graph into this kind of a transaction database by just saying, instead of having, let's say, Mirka Federer lives in Bottmingen, you introduce a class, people living in Bottmingen, and say that Mirka belongs to this class. This way, you essentially, map your graph into a transaction database, and you could apply the same techniques as were developed in data mining. So, essentially, here again, in the data mining community, there were the same exploration of search space from general to specific, but for more, concrete kind of objects. For instance, buying, let's say, just 1 apple is more general than buying apple and beer. Right? And this is essentially the same principle of creating this kind of a lattice. So now, what about going further into graphs? So the other way, instead of transforming the graph into the transaction database, would be to actually search for patterns in the graph itself. This is the concept of a relational association rule learning. What do we do here? Well, essentially we issue a query, like an SQL query, written in a logic-based fashion on the slide, and count how many answers we get. Then if we, let's say, split the query into 2 parts, we could get the head and the body of this rule that the query corresponds to. So for instance, we just count how many married people live together and divide that by the number of, let's say, people who are known to be married, but they are not known to live together. So, and essentially you, in the same fashion, traverse the lattice of relational structures. Right, so let's just maybe go into the specific examples for the knowledge graphs themselves in this context. So this was a, kind of a brief introductory material of what is at all out there. And of course, we would want to reuse some of the techniques from classical inductive learning. So, consider the following graph that depicts married people and living places. For instance, here we see that Brad is married to Anne, and they both live in Berlin. And some other information about some other couples. So this closed world assumption states that whatever is not known is false. That is, for instance, we do not know that Alice lives in Berlin. This information must be probably false. And classical techniques would then state, well, essentially we see that potential patterns reflecting the respective rule correspond to triangles in this case, and there are 4 triangles altogether. But in 2 out of 4 triangles, we actually observe what is stated in the rule. And 2 cases do not follow our rule. So then the rule with respect to this particular graph will have a certain confidence, as it is called, reflecting how well it actually fits the data. So confidence of this rule will be 1/2. Now, well, what you could do is, for instance, apply this rule to predict potentially missing facts. So you will predict that Alice most likely lives in Berlin with her husband, and the same holds for David, right? So now, alternative technique or alternative way of penalizing the rules was recently proposed, which essentially states that we want to penalize only the cases where the respective relation is not known for an individual. So for instance, if at least one living place of Alice is already known, we assume that all living places are known. So, and then basically we will not penalize the rule for Alice, but we will penalize it for Dave in this case. And the respective value reflecting the quality of the rule will be 2/3 in this case. Now, this AMI system, the link is provided on the slide for the system itself. It could mine rules from knowledge graphs by exploiting 3 refinement operators. These are the ones that we've seen before already from 90s, but more restricted ones that target more kind of suitable rules for the specific data. So here we will add a certain dangling atom, add a closing atom, and add an instantiated atom. So these are essentially operators using which you would loop over all possible hypotheses and explore the search space this way. So now what happens is this approach does not really handle the negations or exceptions. And it would be interesting to see how we can extend it. And this is what we did in our previous work, essentially. So here, what we try to do is not only explore the search space of hypotheses and find these frequent correlations, but also try to explain why certain parts of the data do not actually follow our rule. So in this case, the explanation of why certain links are missing could be the fact that the both people for whom the living place is not as expected are researchers. So that could be an explanation. And what we essentially try to do is the following thing. So given a certain knowledge graph, we imagine that there is this ideal knowledge graph that stores all possible facts that hold in the world, which is obviously unknown. So now if we have a set of rules without exceptions, that would be so-called Horn rule set, we make predictions using this rule and get the area with the red border, essentially. So we have the available graph, its superset is the ideal unknown graph. We have the positive rules and make predictions, the area with the red border. Now, what we want to get is to revise this set of positive rules by adding exceptions, negated atoms, such that whenever we do that, obviously the set of predictions becomes smaller. What we want to achieve is to maximize the area within this unknown graph, that is the correct one, and minimize the one outside. So to essentially get rid of incorrect predictions made by positive rules. Pretty natural. And how we do that is as follows. So essentially imagine that we have a certain rule, the one that we've seen already before, stating that married people live together unless one is a researcher. So intuitively, this rule is a good one if there are sufficiently many people among whom one is a researcher and they do not live together. So we can rewrite this rule into the one that states exactly what I've just said. So we could actually do it for various types of rules that were mined by our system and that predict lives-in relations. Now what we say is that for every rule, added exception is good whenever, if we apply all rules in our set, including these rewritten ones that predict negative facts, we have a very small number of conflicting predictions. And this is essentially the objective that we would introduce in order to get the rules with relevant exceptions. So what we want to get is rules with these good exceptions that make as few conflicting predictions as possible. Right. So, and that was the work that we've done and that was published in several papers, where our objective is to maximize descriptive quality of a given rule set and minimize the number of conflicting predictions within the process of introducing these additional negated atoms. So let's go through an example. So if we have a graph as depicted on the slide that is an extension of the one that we've seen before with married relations and living places, here we could see these blue triangles, which reflect the fact that married people do live together. And the triangles with the red border, they are the cases which we need to explain. What are the reasons behind the fact that these respective parts of the data do not follow the rule? So, and when we pre-compute all of these exceptions, what we get is that we get a rule and all exception candidates. But obviously, there could be many noisy things among these exceptions, simply because the data is missing. So in order to get rid of that, what we do is we then consider the whole set altogether and try to minimize these conflicting predictions made by this rule set. And this way rank exceptions in a heuristic-based fashion. So just to give an intuition of what kind of rules we got from the real data, let me just say briefly about the experimental results that were obtained. So what we did is that we took the available knowledge graphs extracted from IMDb. This is a well-known resource with movies. A movie data set, and a Yago ontology extracted from Wikipedia, which contains millions of facts over roughly 100 relations. So we took this available graph, removed 20% of the data for both of these data sets, and mined the Horn rules, these positive rules, incorporated exceptions using our method, and tried to see among those predictions that were made by the positive rule set and were not made by our rule set, how many of them are actually indeed incorrect predictions, which would witness that our exceptions are relevant ones for the respective data set. So what we managed to see is that for IMDb, we got rid of around 60% of incorrect predictions, and for Yago, that was roughly 85%. So the code is available with the respective link provided on the slide. Right. So just a quick maybe feedback. So am I not too fast enough or too technical? Is that fine? Okay, perfect. So you could follow and everything. Right, perfect. Great. So let's then move on. Well, what kind of examples we obtained from these available knowledge graphs? So one was, for instance, that plots of films in a sequel are written by the same writer unless a film is American. Well, Batman 1, Batman 2, Batman 3, I typically well, sometimes are actually produced by several different producers, as if the film is American. So now, another thing is that spouses of film directors appear on the cast unless they are silent film actors. This was another rule that we obtained from IMDb dataset. Well, I mean, you would be questioning, this is a questionable rule. And indeed, it is pretty questionable, and the reason for that is that simply, for old silent movies, maybe some of the data was not really present, something is absent, some things are incomplete, and of course, the rules themselves do reflect bias in the data. The question is, how can we exploit additional information in order to see what kinds of facts are missing and what kinds of facts are actually present? So what parts of the data are complete and what are incomplete with respect to our graph? So this is the next question that we are going to go through. So this is the question of this incompleteness. How can we incorporate additional completeness or incompleteness information present in the data inside the process of rule extraction? So, for instance, if we see the graph with the following topology, which states has sibling, has parent, and has child relations, pretty natural, we proceed with a frequent pattern discovery and get a rule stating that, well, those children who have the same parents, they are basically siblings, right? Natural rule, we predict missing facts, all is good, and we have a certain confidence for this. That is 1/2 in this case. We have another measure that is this partial completeness assumption confidence, which is 1. This partial completeness assumption is the same as local closed world assumption introduced by Google some time ago. It's basically the same notion. Right, so now other graph that depicts exactly the same topology, but due to the missing data, would lead to totally nonsensical rule, which essentially would state that if one is studying at a university where you teach, he is typically your child. Total nonsense. Again, this is this correlation, but the structure of the graph is exactly the same as previously. So it predicts incorrect facts, but has the same measures. So measures-wise, it is exactly the same as the previous rule. Right. What if we knew parts of the graph that are complete and parts of the graph that are incomplete? So we know additional information about what kind of facts are actually missing in the graph. Could we exploit that in order to mine better rules? And that was the question that we answered in our other work on the Semantic Web conference. So what kind of information that would be? Well, you see on the slide the area with the black border, stating that John has 2 children that are known in the available graph. So there is another child that is present in the ideal graph, that is the one that stores all correct facts in the world. So from that we could say, well, we might not actually know that John has this additional child, Mary, but what we could know is that John has 3 children. Altogether, John has 3 children, and we know 2 of them. This additional information is already actually quite useful in order to get rid of these erroneous, strange rules, as we have shown in our experiments. You might be asking, where could this information come from? Well, actually, you could extract it from text, because very often things are mentioned on the quantity level. For instance, things like John has 2 children could be stated in text somewhere. If you mine this information explicitly, you could get these completeness statements. So you would know how many should actually be in the graph. I mean, this holds the same for domain-specific knowledge graphs as well, of course. So if you pre-mine this information from text and then exploit it further in the rule induction process, that might help. There are other works that deal with this completeness question. So there is previous research which we could actually reuse in this context. And basically, we introduced the novel notion of completeness confidence, which would penalize rules that predict new facts in incomplete areas. So it would penalize rules that do not it will not penalize rules that predict new facts in incomplete areas, right? So that is this incompleteness information that we would then exploit. It basically generalizes the standard notion of the confidence that was proposed in the data mining community, and also generalizes this partial completeness assumption confidence that we have earlier seen. And then there were also several other measures that could help us in this context to, rank these rules to get the most relevant ones, the most likely ones, like precision in this case, which will penalize rules that predict facts in complete areas, or ratio of missing facts filled by a rule. This is a recall, completeness-aware recall. Some proportion of predictions in complete and incomplete parts of the graph. That would be the directional metrics, and several other measures. So there are many measures that could then be used in order to then incorporate into the rule learning process additional information about quantities coming from text. So there is a software which exploits these measures and allows one to actually learn rules from your knowledge graph with incompleteness statements, and it is freely available online. So that was developed as part of our project. Right. So now, of course, there is another thing. Can we actually learn rules from hybrid sources? That is, we have structured knowledge and also unstructured textual knowledge additionally. Could we somehow incorporate things and learn rules jointly in this context? So as we have seen before, since this ideal knowledge graph is not available for us, maybe we could somewhat learn information about it by incorporating what is known from other sources. So what if we actually did have this ideal knowledge graph? Of course, we would have ranked our rules perfectly. We would not have had this bias issue in the data. So if there is some kind of a measure mu that allows one to estimate the quality of a rule on this ideal graph, that would be great. As we know, unfortunately, the ideal graph is unknown, but what is actually known or could potentially be known is a probabilistic representation of this ideal graph. If we do have a probabilistic representation of the ideal graph, in fact, what we could do is to measure the quality of our rules not only on our available graph, but also on the probabilistic representation of the ideal graph. This formula mu reflects exactly what I have just said, with some weighting factor lambda. You might be asking, but where will we get the probabilistic representation of the knowledge graph? Actually, knowledge graph embeddings are a very helpful way of getting such information. This is going in the direction of words-to-vec, but essentially embeddings that were proposed for knowledge graphs. Let me just briefly state what they are actually about. So intuitively, if we are given a knowledge graph as depicted on the slide, what we are aiming at is finding vector representations of every node and every relation in a low-dimensional vector space, such that for every node, it holds that the vector for this node plus the vector for a relation is roughly close to the endpoint to which this node is connected to the relation. Or if we talk about subject, predicates, and objects, this would be the formula exactly as presented on the slide. Intuitively, here, the error of translation of a true knowledge graph fact should be smaller by a certain margin than the error of translation of the fact that is not present in the graph. So this is roughly the representation of what we want to achieve. Now, interestingly, this has been extended also by textual resources. That is, if we have additionally also information about descriptions of entities present in the knowledge graph, like in this case for Miami. Miami is a major port city on the Atlantic coast, for instance. Then this information could also be incorporated in our knowledge graph embeddings. Additionally, from the textual descriptions of entities, we could in fact also incorporate textual information that contains mentions of different entities. So basically, co-occurrences of entities generally in the text could also be incorporated in this embedding approaches. And there were so-called TECE and SSP models proposed recently. What that means is that embeddings is a very nice way of incorporating information from different hybrid sources in order to predict potentially missing facts and create a probabilistic representation of our so-called ideal graph, that one that we are aiming at. And what we did in our work last year is we exploited exactly this information for rule extraction. That is, what we are having here are text documents that together with a knowledge graph are being exploited in the generation of a knowledge graph embedding that is being treated as our ideal graph. And during the rule construction process, our rule search space is being guided by additional information coming from the embedding space. So here we have two components, this rule construction component and the rule pruning component, which helps us to exactly control the traversal of hypotheses. So now the rule pruning here would do the following. So basically, during the process of this hypothesis construction, using operators similar to the ones that we've seen before, plus also operators for adding negated atoms, we would prune the rule search space relying on our hybrid measure that relies not only on the original graph, but also on the probabilistic representation of the ideal graph given by knowledge graph embeddings, which are possibly enhanced with textual information. Right. So we have actually evaluated this approach on a free base, which stores around 600,000 facts, over 15,000 entities, and roughly 1,500 relations, and also over Wikipedia, Wikidata dataset with around 250,000 facts. So for the training graph, we removed 20% of the data from the available graph, and then essentially exploited various embeddings. In this work, we used the trans-C embedding. This is the classical, standard one, also Holy, and the text-enhanced one, SSP model. And our goal was to evaluate how well our hybrid measure that exploits this probabilistic representation of missing facts actually, helps us to get better rules. And we have got very interesting results. So what is present here is the average precision of the obtained rules, where on the x-axis we see the lambda, that is the factor that controls the weight put on the part of the measure coming from embedding. So that is for lambda equal 1, we are relying only on the embedding model in ranking our rules. And for lambda equal 0, we only rely on the original knowledge graph. And we see a very interesting observation that especially for SSP model, that is the text-enhanced one, there is this interesting increase in the precision when we incorporate this additional information in the rule ranking phase. And there is a clear positive impact in all cases starting from lambda equal 0.3. If we compare to state-of-the-art rule learning systems for knowledge graphs, that is the EMI system, which I've already mentioned before, we could see that there is a clear improvement. And the case for the EMI system, that would be the case where lambda is equal to 0. So this actually motivates us to incorporate more information coming from the machine learning models or hybrid models that are enhanced with different information resources and treat them as our probabilistic representation of the knowledge graph. And interestingly, here we can plug in not only a single embedding model, but also aggregate information over several embedding models. So this is pretty, convenient fact. Right. So now you will be asking, where can we actually exploit this kind of rules that we have just learned? Apart from the fact that the apart from this prediction information. What we did in our next work is using these rules for other purposes. But before going further into details, I just wanted to show you some examples extracted from Wikidata. The first one states that script writers stay the same throughout a sequel, but not in the case for TV series. And the other one states that nobles are typically married to nobles, but not in the case of Chinese dynasties. So some correlations in the data that are actually aggregated over a lot of information from encyclopedic knowledge, and that shows pretty interesting results. So now the further application of these kind of rules that are being extracted from the data is in the context of fact-checking. So this is, let's say, a complementary direction to the direction of fact prediction in knowledge graphs. So prediction would just mean, well, we take the rules that we have obtained, we predict and obtain potentially missing facts. But they themselves are also very interesting from, let's say, the structural perspective, because they show some quite fascinating correlations in the data. So now, what kind of other things could be done? So actually, with some colleagues from Max Planck and Amsterdam University, so we developed a framework that allows one to check facts, check the truthfulness of facts by exploiting query rewriting over hybrid sources. So what we see here is we see a query over some non-prominent relation. For instance, Hawking is influenced by Dirac. Well, I mean, typically it might not necessarily be explicitly stated in text, for instance. That is why it might not be transferred to the knowledge graph. But what we could have are some additional inference rules that could potentially allow us to evaluate the truthfulness of this specific fact by aggregating information from structured resources, like from a knowledge graph, and from text simultaneously. So, for example, you could state, well, people are typically influenced by one another if they have, if one is an academic advisor of another one. Or you could say that if a person, for instance, wrote a certain novel and another one was very much impressed by this novel, then he might likely be influenced by that person. I mean, these are more, general examples. But imagine, for instance, collaboration questions. You want to find out whether within a company, one group of people collaborates with another group of people somewhere. And this information is hidden first in the textual documents that are present, second in databases that are out there. So could you aggregate, actually, that all together and use rules that allow you to semantically link bits and pieces of this data and then answer the question that is being posed? So this is this framework that has been developed in our university. And then, so far, what it supports is it supports the knowledge graphs Yago and Wikidata. It allows for elastic search over Wikidata and also uses the Bing API to query web resources and allows the users to provide these rules, like positive Horn rules, or also mine them from the knowledge graph using the methods that I have presented before. So we can mine, for instance, rules from one knowledge graph and then exploit them further in this query answering framework in order to link semantically different pieces of information across knowledge resources. So, and what it does internally is it rewrites the query that was given as input using techniques coming from SLD resolution. This is logic-based methods from the 70s proposed by Robinson, extended by external resources, external textual resources. So it's basically query rewriting method with external Oracle support. And in the output, it returns us an explanation that states why a certain fact is true. So that would essentially state within the explanation the fact, pieces of knowledge coming from a knowledge graph, some text snippet with its link, relevant rules that were used for deriving the specific knowledge and a certain confidence value. And we have shown that compared to state-of-the-art fact-checking methods, we actually have a double increase in recall, and precision is roughly preserved. So this is one of the possible, further applications of rule learning methods. For instance, you could kind of accumulate rules provided by domain experts explicitly with these learned rules from knowledge graphs. Right. So let me just summarize the things that were presented so far. So what we've seen is various classical rule learning methods from inductive logic programming. So basically the key techniques that are being used in this context. Approaches for learning rules from knowledge graphs that not only exploit the search space to get the positive rules, but also incorporate exceptions in the rules that are learned. And we considered some of the further applications for rule-based fact-checking that allows one to exploit rules in the reasoning process to estimate the truthfulness of the fact and also aggregating information over structured and unstructured resources. Right, and finally, if you're interested in this kind of research and looking for a PhD position, for instance, then we're also hiring at Bosch Center for Artificial Intelligence, and I will be very happy to talk to you about that further. And then maybe I'll let a little bit more time for questions and further discussions if you have any, because they were not asked during the talk. So thank you very much for your attention, and I hope that was not too complicated to follow.